Hi, everyone. I hope you're ready for a shift to more biological talk. All right, so I'll be talking about a group here at UCSD that's we're working on developing a diagnostic device for HIV treatment failure detection. Okay, so in the US, patients on HIV therapy are tested every 3 to 6 months to make sure their treatment is continuing to be effective. This allows doctors to change their medication if HIV has developed drug resistance to the current medication and is no longer blocking HIV from replicating. Here you can see a graph of the progression of HIV. The viral load is shown in yellow, and this is the amount of virus that is found in the blood plasma, which is the liquid component of blood. If a therapy is effectively working, then it's causing HIV to be dormant and stay in the cells and not enter the blood plasma. So you can see here, when antiretroviral therapy is administered, the viral load goes down. But if someone has developed treatment failure or drug resistance, the viral load goes back up. Now, this is a serious problem. The tests that detect viral load are called viral load tests, and they cost roughly $80,000 in equipment and $65 per test. Unfortunately, $80,000 is a serious cost constraint for rural hospitals. This has prevented many doctors in the developing world from providing continuous monitoring for their patients on HIV. If a patient wrongly believes that their medication is effectively combating their HIV, then this was a problem not only for their own health, but also for some people around them. They will get sick if they're not switched to an effective medication, but they could also pass on this drug-resistant strain of HIV to others, causing an overall decline in the efficacy of first-line therapies. And these are the therapies that are most widely distributed in the developing world and the most low cost. At Engineering World Health, the student organization of which I've been co-president for the past year and a half, we have partnered with Maputo Central Hospital in Mozambique, Africa, to design a diagnostic device to detect HIV treatment failure. Our device is only $2,000, which is 2.5% of the cost of current technology. Now, you may be wondering how we were able to bring down the cost so much. Well, our device has a simple yes or no output. This contrasts current technology, which counts precisely how many copies of HIV is found in the blood plasma. So you may think, well, isn't it important to have this quantitative value? For some applications, it is, but when you're detecting treatment failure, all that matters is if there's any HIV in the plasma or if there is none, and that's exactly what our test determines. Here you can see the 4 components of our device. We're obviously in a prototype stage, and I will tell you a little bit about the overview of how each of these works. The first device on the top left is a centrifuge. This processes the blood. The next step is a pump system to extract and purify the RNA. The third, on the bottom left, is a thermal cycler that runs a polymerase chain reaction that can amplify a gene specific to HIV. And lastly is a gel box that runs gel electrophoresis to visualize the results. And now for a little more detail. Don't feel bad if you don't understand. It's a little biological, but I'll try to break it down. So when you take a blood sample from a patient, the first step is to isolate the blood plasma, as I mentioned before. So what we use is a centrifuge, and using the rotations, the high-speed rotations, this creates a force that separates the cells from the liquid component of blood. And now, as I mentioned before, if a treatment has failed, then there will be virus in this blood plasma. So the next step is to extract the RNA. HIV is an RNA-based virus, so if there's any HIV present, there will be HIV RNA present. So that's why we extract the RNA. But there are many reasons to have RNA in your blood that have nothing to do with HIV. And for this reason, we have to see if there's any HIV-specific RNA. And for that, we use a polymerase chain reaction. And what that does is amplify a gene of your choice. And we have chosen a gene that's specific to HIV and only found in that virus. So if anything is copied in this reaction, that means that there was virus present. But if there was no HIV virus present in the sample, then nothing will be copied at the end of the reaction. So then all that's left is measuring if there's any product or if there's no product after this reaction has completed. And for that, we use gel electrophoresis. Now, this process itself isn't a novel idea, but what we're doing is making it accessible to these rural hospitals. The 4 main criteria that we keep in mind as we're building our prototypes are crucial to make this effective in a rural hospital. So first, we want the device to be inexpensive so that they can afford buying it in the first place. But secondly, we also want it to be easy to use so that low technician training is required, and this will allow it to be accessible to even wider population. The third criteria is for it to be sustainable, and we're addressing this by using easily replaceable parts. And we're also making easy-to-use manuals, so if anything goes wrong, they can get the parts and they can fix it. Lastly, we need our device to be as precise as current tests. The most exciting part of our device is its versatility. The separate components of the device can be used independently as key elements in a hospital lab. For example, a centrifuge is crucial in many lab tests in order to perform separation or filtration of a sample. In addition, the device as a whole can be used and adapted for different diseases. If you can recall what I mentioned before, the polymerase chain reaction amplifies a gene specific to HIV in our diagnostic device. But you can have the polymerase chain reaction easily detect and amplify a gene specific to a different disease, and that'll create the diagnostic device to detect this different disease. So this is very easily adapted, and we're excited to move forward and try to use it for diseases other than HIV. We're moving forward at a very fast pace, and we're excited to see how our device will affect HIV monitoring in the developing world. I feel like it's important to mention that I'm not doing all of this on my own. We have a team of 30 undergraduate students that are working on the separate components of the device. We also have people focusing on the important responsibility of finding out how to distribute and manufacture the completed products. In general, our organization runs like a small startup. We have multiple weekly meetings, our members present about their progress, and we're constantly applying to grants and competing for funding. This is an old picture of our team from 2 years ago. So I'd like to end with saying that I'm so thankful that I found Engineering World Health as a freshman, because it's provided me and my peers not only with an opportunity to make an impact far past this university's campus, but also it's been a tremendous learning experience. By being on the project team, I've learned technical engineering skills. I've learned leadership skills from leading the teams, and most importantly, I've learned how engineering can be used to solve public health issues. The message I would like to leave you with today is that undergraduate students, with the right environment and with the right support, can make a difference, and we are making a difference. Thank you for your time.